BERT, Reading in Both Directions, Part 2. The landscape BERT emerged from. In Part 1, we saw why unidirectional pre-training was holding back language understanding tasks. The constraint was clear. Models like GPT could only see context from one direction, and models like ELMo combined two separate directions but didn't fully integrate them throughout the model. Part 2 is where we examine the landscape BERT emerged from. We'll look at 3 research tracks, what each achieved, and why none of them quite solved the bidirectionality problem. By the end of Part 2, you'll understand the evolution from static word embeddings to deep bidirectional pre-training, and why BERT feels less like an incremental tweak and more like a culmination. Before we dive into BERT's architecture, we need to understand the world it arrived into. Because here's the thing, BERT didn't appear in a vacuum. It was the product of years of researchers chasing one core question. How do we teach machines to understand language the way humans do? By 2018, the answers clustered into 2 main tracks, plus a third route via supervised transfer. Track 1, the feature-based approach. Learning representations from scratch was inefficient. For a long time, NLP systems learned representations from scratch for each task. It worked, but it was inefficient. Every new task had to relearn language from near zero. It's like teaching someone French vocabulary from scratch every time they pick up a new French book. Then came the breakthrough, pre-trained word embeddings. Word2Vec and GloVe changed everything. These methods learned representations of words from massive amounts of unlabeled text. Large text corpora like Wikipedia, Common Crawl, news, books. And suddenly, every NLP system got better. Sentiment analysis improved. Named entity recognition improved. Question answering improved. Pre-trained embeddings became foundational to modern NLP systems. But there was a problem. These early embeddings were context-free. The word bank had one representation whether you were talking about a riverbank or a financial bank. The word bow meant the same thing in take a bow and bow and arrow. This is obviously wrong. Humans don't understand words in isolation. We understand them in context. Researchers generalized the approach. Instead of just word embeddings, they created sentence embeddings, entire sentences compressed into vectors, and paragraph embeddings, same idea, longer text. Some tried training models to predict the next sentence. Others used left-to-right generation. Given the previous sentence, generate the next sentence word by word. Some even experimented with denoising autoencoder objectives, where you corrupt the text and train the model to reconstruct it. Then came ELMo, the game changer. ELMo, embeddings from language models, took a major step forward. They extracted context-sensitive features from both a left-to-right and a right-to-left language model. Here's the clever bit. The contextual representation of each token was the concatenation of the left-to-right and right-to-left representations. So now, bank near river would have a different representation than bank near account. The model could see both directions of context. When researchers integrated these contextual word embeddings into their existing task-specific architectures, they advanced the state-of-the-art across several major NLP benchmarks: question answering, sentiment analysis, and named entity recognition. There was just one catch. ELMo is feature-based, and it isn't deeply bidirectional. It combines left-to-right and right-to-left signals, but the two directions don't jointly condition on each other during the same pass through the network. Let me make this concrete. Imagine reading a sentence. The riverbank was muddy. The left-to-right model processes the, then river, then bank. By the time it hits bank, it's seen river, but hasn't seen muddy yet. It makes its best guess about what bank means. The right-to-left model processes muddy, then was, then bank. By the time it hits bank, it's seen muddy, but hasn't seen river. It makes its own guess. Each direction is computed separately. One only sees the left context, the other only sees the right. The final token vector contains both signals via concatenation, but the model does not learn left-right interactions through a single jointly bidirectional computation at every layer. It's closer to look left, look right, then combine, rather than genuinely integrating both directions throughout every layer. That's what BERT changes. Why does this matter? Because language understanding often requires seeing the complete picture simultaneously. You can't fully understand a word by looking left, then looking right, then stitching the views together. You need to look both ways at once. Track 2. The fine-tuning approach. A different philosophy emerges. While the feature-based camp was improving embeddings, another group of researchers asked a different question. Why freeze the model and treat it like a feature extractor? Why not pre-train a model end-to-end, then fine-tune the whole thing for the target task? Early versions of this idea mostly stopped at pre-trained embeddings. Later work fine-tuned full encoders. The encoder revolution. More recently, researchers realized, why stop at words? Why not pre-train entire sentence or document encoders? These encoders would produce contextual token representations from unlabeled text, then get fine-tuned for supervised downstream tasks. The advantage? Few parameters need to be learned from scratch. This is massive. Think about the numbers. With traditional supervised learning, you might have 10,000 labeled examples for your specific task, like question answering. You're trying to teach a model both what language is and how to answer questions, all from those 10,000 examples. With pre-training and fine-tuning, the model first learns from billions of words of text. It learns grammar, semantics, how words relate to each other, what sentences mean. Then you fine-tune on your 10,000 examples, and all you're teaching is the specific task, how to answer questions. The model already understands language. That's the difference between learning everything from scratch versus transferring knowledge. OpenAI GPT became a flagship example of this philosophy. It used left-to-right language modeling as its pre-training objective. Given prior tokens, predict the next token. Then it fine-tuned for downstream tasks and achieved previously state-of-the-art results on many sentence-level tasks from the GLUE benchmark. But there was still a fundamental limitation. GPT could only see what came before each word, never what came after. This is like trying to understand a mystery novel where you're only allowed to read forward, never flip back to earlier clues. You might catch some connections as they happen, but you'll miss the patterns that would be obvious if you could see the whole picture at once. This matters most for token-level understanding. Tasks like named entity recognition, span-based question answering, and coreference, where the representation of each token benefits from both left and right context. GPT demonstrated the power of fine-tuning, but it was still unidirectional. It could only see half the picture. Track 3. Transfer learning from supervised data. Not all pre-training happened on unlabeled data. Some researchers showed you could effectively transfer from supervised tasks with very large labeled datasets, too. Examples include natural language inference datasets, where you have hundreds of thousands of labeled examples of whether one sentence entails another. Machine translation datasets, where you have very large collections of aligned sentence pairs. Computer vision research had already demonstrated this. You could pre-train a massive model on ImageNet's million labeled images, then fine-tune it for your specific vision task. The recipe worked. The question was, could this work for language too? It could. But there was a catch. You needed those large labeled datasets to exist for something related to your target task. And for most NLP tasks, they didn't. Legal, medical, and specialist domains often don't have huge public labeled datasets, and privacy constraints can make them impossible to build. So supervised transfer learning was powerful but limited in where it could be applied. BERT's unique position in this landscape. This is where BERT lands, and why it feels like a synthesis of what came before. The feature-based approaches, like ELMo, gave us context sensitivity, but didn't deliver deep unified bidirectionality throughout the model. They let the model look left, then look right, then combined the views. But they never let the model look both ways at the same time. The fine-tuning approaches, like GPT, proved the power of transferring a pre-trained model, but remained unidirectional. Like reading that mystery novel with half the pages torn out. Supervised transfer worked well when massive labeled datasets existed, but that requirement created a bottleneck for most real-world applications. BERT does something different. It pre-trains deep bidirectional representations from unlabeled text by jointly conditioning on both left and right context in all layers. Not looking left, then right, then combining. Not processing left to right, and hoping the model figures it out. Genuinely, deeply bidirectional. Seeing the complete context simultaneously at every layer. And it does this using only unlabeled data. Billions of words of text from English Wikipedia and books corpus. No massive supervised datasets required. No bottleneck. The pre-trained BERT model can then be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of tasks. Question answering, sentiment analysis, named entity recognition. The punchline is simple. For the first time, a model could represent each token with full surrounding context baked in at every layer and transfer that capability broadly. That's what the previous tracks were all reaching toward, but never fully achieved. The result! BERT achieved state-of-the-art on 11 NLP tasks. It didn't just improve incrementally on previous benchmarks, it shattered them. At first glance, the gains look almost too big, so it's natural to ask what changed. The answer became clear. For the first time, a model could genuinely see the full context, past and future, beginning and end, simultaneously at every layer. That's what deep bidirectionality gave us. In Part 3, we'll see exactly how BERT pulls this off. We'll unpack the architecture, the pre-training objectives that make deep bidirectionality possible without cheating, and why masked language modeling turned out to be the missing piece everyone had overlooked. We'll also look at next sentence prediction and how BERT learns relationships between sentences, not just word-by-word patterns.